point out at this time. Okay, so last time we were looking at various types of spin states. We found eigen states of the Sx, Sy, and Sz operators, and we started out to look at the eigen states of an operator in some general direction in the xy z space. Okay, so suppose this is some unit vector n. Okay, so it's going to have components. It's going to have an x component, y component, and z component. Okay, based on these angles, theta and phi. So the unit vector is going to have a z cosine theta. The others will be proportional to sine theta. So sine theta cosine phi, and y direction sine theta sine phi, right? Okay, so that's a certain vector in the in this direction. Now, what I want is the spin vector in that direction. So what I do is I take the dot product of this object with the s vector. Okay, what is the s vector? It is the Sx operator in the x direction, Sy operator in the y direction, and Sz operator in the z direction. Okay, so very simply you just get the various components. So you get cosine theta times Sz plus sine theta sine cosine phi Sx plus sine theta sine phi Sy. Okay, and you can check very simply that, for example, if you put theta equal to 0, you are going to get the Sz vector. Okay, to get the Sx vector, you have to put sine theta equal to, theta equal to 90 degrees and phi equal to 90 degrees. Well, phi equal to 0 will give you Sx, phi equal to 90 degrees will give you Sy, right? So now I have all of these things in. So what I want to do is now write the matrix form of this. So I'm going to get Sz multiplied by cosine theta. Now all of these matrices, Sx, Sy, and Sc, have an h bar over 2 associated with them. So let me put that down first. And then I have Sz, which remember was 0, 0, 1, minus 1. Okay, so multiplied by cosine theta, that gives me cosine theta here, and a minus cosine theta there, right? 0, 0. Okay, so what about these guys? Okay, so Sx was 1 and 1. So it's going to be sine theta. Well, maybe it's not going to fit, so let me just expand my matrix. Okay, so something like this. So minus cosine theta. And I have 1 and 1 here for Sx, remember? So it's going to be sine theta cosine phi, and sine theta cosine phi, okay, for the 1, 1 elements, right? So just remember these matrices, sigma z, which is just Sz without the h bar over 2, is 1 minus 1, 0, 0. Sigma x is 0, 1, 1, 0. and sigma y is minus I, 0, I, 0, right? Okay, so I'm just multiplying these things by the prefactors and just adding them up. So the last thing that remains is the sy. So that also has a sine theta. Okay, so it's now going to bring in a sine phi. So it's going to bring in a minus I sine phi. Okay. On the other side, it's going to bring in a plus I sine phi. Okay, so this is our Sn, if you like. Okay, that's our matrix. I can also group these things into somewhat more compact form. I can write this as e to the I phi, and I can write this one as e to the minus I phi. Okay? So that's our spin matrix. Again, what we do is we look at the eigenvalues and their eigenvectors. Okay, so let's just look at it without the h power over 2. I'm going to be interested in cosine theta minus lambda and minus cosine theta minus lambda. What should I find for the lambdas? What will be the eigenvalues of this object? This doesn't involve calculation.
H bar over 2 minus H bar over 2.
Okay, h power over 2 and minus h power over 2. Why? Because it's a spin object. Okay, it's a spin 1/2 object. No matter which direction I measure the spin, I can get only two values, plus h power over 2 and minus h power over 2. So this matrix without the h power over 2 should give me plus or minus 1. Okay, so over here I have sine theta e to the minus I phi and sine theta e to the plus I phi determinant. So what do I get? I get cosine minus lambda multiplied by a minus cosine theta, I forgot the theta, plus lambda, okay, and minus sine squared theta. The phi pieces cancel out. So I'm going to get minus lambda squared, well, other way around, minus cosine squared theta minus lambda squared minus sine squared theta. So cosine squared plus sine squared is 1, and I end up with lambda squared minus 1 is equal to 0. So indeed I get lambda equals plus or minus 1. Again, okay, for possible results of measurement, plus or minus 1 multiplied by h power over 2. Okay, so everything is nice and consistent. Let's find the eigenvectors. The eigenvectors are, okay, so I have to just solve a simple equation, cosine theta sine theta e to the minus I phi, sine theta e to the I phi minus cosine theta. Okay, this thing multiplied by a vector, again, my favorite vector, 1 and a, is going to give me one of these eigenvalues. Let's take lambda equal to 1 and a. So we are looking at the lambda equal to 1 case. All right, so what does that give me? That gives me cosine theta plus a sine theta, okay, and e to the minus I theta, I phi, is equal to 1. Okay, that's what the first equation says. So this says A is equal to 1 minus cosine theta divided by sine theta and multiplied by e to the I phi. All right? So that's my eigenvector for lambda equals 1. Okay, so I'm going to get 1 and 1 minus cosine theta divided by sine theta e to the I phi. Okay, so I need to normalize this, but I sort of see a pattern here. I can look at various terms here. For example, if I look at sine squared theta over 2, it's going to be 1 over 2, 1 minus cosine theta, right? Because I have to take twice the angle. And I can also look at something like, okay, the cosine of this, we are going to need this also. Cosine squared theta is 1 over 2, 1 plus cosine theta. And if I look at sine theta over 2, cosine theta over 2, that gives me just 1 over 2 sine theta, right? Okay, so these are just certain trigonometric relations. And what I'm going to do is I'm going to write this denominator in a form, so I'll try to make it more symmetric in the two components. So 1 minus cosine theta is 1 over 2 sine squared theta over 2 divided by sine theta over 2 cosine theta over 2. That also has a 1 over 2 in front. Okay. And I still have the e to the I phi. So 1 factor of sine theta over 2 cancel, the 1 over 2's cancel. So what I'm going to do is I'm going to multiply both the numerator and denominator by cosine theta over 2. Okay, so yes.
Isn't 1 minus cosine theta equals 2 times sine squared?
Mm-hmm.
It's not 1 over 2 times sine. 2 times.
Again, tell me.
1
what?
minus cosine theta equals 2 times sine squared theta over 2.
Oh yes, thank you. But they still cancel.
Yeah.
Okay, good. Thank you. Okay, so that's 2, and they cancel. All right. So I'll multiply both the denominator and numerator by cosine theta over 2. So this is proportional to cosine theta over 2 and sine theta over 2. I'll also multiply both the numerator and denominator by e to the minus theta over 2. So e to the minus I phi over 2, sorry. So that leaves e to the I phi over 2 here. Okay, so this looks a little bit more symmetric. I have just multiplied the elements of the vector by some constant. Okay, theta is some constant. So I get these terms, so it looks more symmetric. And it's also explicitly normalized. Cosine squared plus sine squared is going to give me 1. Okay? And you can also check various limits. For example, if you put theta equal to 0 and phi equal to 0, you are going to get 1, 0, which is the vector, remember, for the x direction. Okay, so maybe I'll just list them a little bit over here. Okay, so remember that up z, okay, is associated with 1, 0. Down z is associated with 0, 1. For example, up x is what? Remember? Well, I should assign you more homework, I think. 1 over root 2, 1, 1. Okay, down x is 1 over root 2, 1 minus 1. Okay, so you can just check for various angles what you are going to get. Okay, so if you, for example, put theta equal to 90 degrees and x equal to phi equal to 0, okay, I'm in the x direction, right? So if theta is 0 and phi, if theta is 90 degrees and phi is 0, we are in the x direction. So let's just check. So if I just put theta equal to 90 degrees, this becomes square root of 1 over square root of 2, 1 over square root of 2, right? And since phi is 0, these things disappear. So indeed, okay, as we should, okay, this is obviously not surprising. We are constructing S out of Sx, Sy, Sz. If we put the proper angles in, then these things should result, okay, to those things. Okay, one thing that's peculiar here, and this will come up again and again with fractional spin systems, you see that things are functions of theta and phi over 2, which means that if you make full rotations, you don't recover the same state. So I start, for example, with phi equal to 0, I get a value. But now if I let phi go to phi plus 2 pi, so if I increase phi by 2 pi, what does that mean? I go around the z-axis once and I come back to the same point. What happens to this object?
Not the same.
Not the same, but there's a simple, okay, they become the negative of what we had earlier. So if you rotate this object around the z-axis once, you get the negative of what we had earlier. Now you might say, how come this can be physical? Well, in any expectation value that we take, remember that we multiply the vector with its adjoint. So we are going to get 2 minus signs, and any average quantity that we will calculate will not be influenced by that. But if we do something like an interference experiment, okay, so if we have the particle coming in one path, along one path, and along the other path it makes a, okay, 360 degrees rotation, and if they interfere, there will be a destructive interference. Okay, so we'll study this again. This will follow us in a few examples that we are going to solve. Okay, so let's also look at the lambda equal to -1 case for completeness. So if you look at the lambda equal to -1 case, I still have the same matrix, which is cosine theta minus cosine theta, sine theta e to the minus I phi, and sine theta e to the plus I phi. So now I multiply this by my eigenvector, something like this, is going to be minus 1a. Okay? So the first line again tells me cosine theta plus a sine theta e to the minus I phi is going to be equal to -1. So now a becomes equal to -1 minus cosine theta, right? Divided by sine theta and then e to the plus I phi. All right, so now the vector looks something like this, 1 and minus, okay, let me write like this, minus 1 plus cosine theta divided by sine theta e to the I phi. So I write this again as 1, okay, minus 2 cosine squared theta over 2, right? And the denominator is 2 sine theta over 2 cosine theta over 2. So this time, one of the cosines in the denominator cancels with the numerator. These things go away. There's still an e to the I phi here. And this is just proportional to, okay, multiplying through by sine theta over 2. I get sine theta over 2 minus cosine theta over 2. And what? E to the I phi over 2, e to the minus I phi over 2. All right, so now that we have these things, we can just sort of play around with what these things imply in terms of experiments. So let's look at that. Suppose I now take some unknown spin state and a bunch of objects, and I measure the spin in some particular direction. Okay, so there are two possibilities. I either get plus h bar over 2 or minus h bar over 2. So the state of the particle, if it comes this way, is going to be what? Up n. If it is going out this way, it's going to be down n. Now I want to make a measurement, okay, of, say, SZ. So now I measure SZ. Okay, again, I have the same two possibilities, h bar over 2 and minus h bar over 2. And now I want to find the probabilities, okay, what the probabilities are. So I have this plus h bar over 2 state here. Okay, so this up n is something which looks like cosine theta over 2 e to the plus or minus I phi over 2 and sine theta over 2 e to the plus I phi over 2. Okay, so now I need to expand this in terms of the eigenstates of the SZ operator. But the eigenstates of the SZ operator are very simple, right? So they are either of the form 1, 0 or 0, 1. So how do I expand this? Well, it's going to be something times 1, 0 plus something else times 0, 1. So the upper component is just cosine theta over 2 e to the minus I phi over 2. The other one is sine theta over 2 e to the I phi over 2, right? Okay, so this is the probability. The magnitude squared of that is the probability of getting this. Okay, so let me call this P up and let me call this P down. So if I square this, I'm going to get cosine squared theta over 2, which will be probability up. If I square that, then that's going to be P down, which will be sine squared theta over 2. Okay, so the measurement probability, so if I just have an experiment in which I send these electrons through, okay, and I adjust my experimental apparatus so that it is measuring the spin in a direction, okay, it's measuring the spin component in a direction which makes angle theta with the z-axis, because that's the only important parameter you see, okay? The phi doesn't enter because I'm measuring the z component of the spin. So I measure the, okay, n component of spin, which makes an angle theta with the z-axis, and then I measure the z component of the spin. And what do I get? The probability of getting, okay, for this case, where if I measure up in this first measurement, the probability of getting up again is proportional to cosine squared theta over 2. So when theta is very small, obviously you are going to get a large probability. In fact, if theta is 0, that means you are just repeating the measurement, right? Then you are just measuring SC. So you are, in that case, you'll definitely get up. What happens if you have something like an angle equal to pi over 2? What does that mean? I have measured the spin in the first instance in a direction which is perpendicular to the z-axis. So it can be x direction, y direction, or any direction on the xy plane. Okay, so theta is 90 degrees. And then I'm going to get here cosine squared of 45 degrees. Okay, so cosine of 45 degrees will be 1 over square root of 2. So in that case, I'm going to get one half probability. But that's something we studied earlier, right? When if you measure the spin in some direction perpendicular, say in the x direction, and then you try to measure the spin in the z direction, you get 50-50 probability. Okay, so that's all consistent. What happens if I turn it all the way around? I turn the experiment upside down, okay, which really means I'm taking the other branch over here. That corresponds to theta equal to pi, and pi over 2 is now 90 degrees, and I get 0 here, okay, for upspin, and I get, okay, 1, probability 1 for the downspin, because now what I am really doing is I am just trying to measure, okay, the other branch, okay, I'm just generating a downspin. Is this clear? Any questions? Okay, let me return to this problem of the phase developing by yes.
I was completing the sentence.
Oh, you are completing. That's what ChatGPT does, right? Okay, thank you. Yes.
For the z measurement, if we have theta equals 0, what should we take for phi?
If theta equals
For
0.
the z measurement. So we found 1 and 0 to be the eigenvector for the z direction.
Okay.
We took theta equals 0, but what should we take for phi?
Okay, if you take theta equal to 0, that corresponds to a strange point in the spherical coordinates. What you are doing is independent of the angle phi. Okay, so you should get the same result no matter what phi is. Okay, so then becomes sort of irrelevant. Okay, so I have been discussing this, okay, making measurements in various directions, but there's a way of actually rotating the spin itself. Okay, if you have a spin, if you measure the spin in a certain direction, you can change the direction of the spin by putting it actually in a magnetic field. So let's discuss that a little bit. We'll probably not be able to finish the problem completely, but there's some important physics in this discussion. Okay, so we have spin in a magnetic field. Okay, so if I take my spin, if I take the electron, and suppose it's not moving so that I don't have to worry about any V cross B forces, but it does have a magnetic moment, right? So the magnetic moment is pointing in some direction. Okay, so magnetic moment and spin are related. We'll see how that happens in a minute. And we put this inside a uniform magnetic field. Okay, so suppose I put it in a uniform magnetic field like this. Okay, so I have a B which is equal to some constant B0, and let's choose it in the Z direction. Okay, so that's what I have. Now, what would you expect? Now, normally, when you have a spin, okay, and angular momentum in a field like this, well, if you have a dipole, okay, right, in a field, if it's an electric dipole in an electric field or magnetic dipole in a magnetic field, there will be a torque on it, right? It will try to change its angular momentum. And the angular momentum it's trying to change is going to be perpendicular to the direction of the original angular momentum, so the angular momentum will precess, right? It will precess around the axis which is associated with the magnetic field. Okay, so that's what we expect classically, but let's see what comes out of quantum mechanics. So we are going to have an energy, Hamiltonian, which is going to have the form minus mu dot B, right? So that's the energy of a magnetic dipole in a magnetic field. And that, since this is in the Z direction, it's going to be minus mu magnitude of mu B Z magnitude B0. Okay, so it's going to be the Z component of mu times B0. Okay, now how do I associate the magnetic moment with the spin? So let's just discuss again classically. Classically, if I have a charged object, right, say charged Q, moving around some center with some velocity V, okay, and has mass m at radius r, so we specify everything. What is the angular momentum of this object with respect to the center? Come on, freshman physics. What is the momentum? Momentum? Okay, mv, and if I multiply it by r, okay, I get the angular momentum. Okay. Now, what about the magnetic moment? Okay, now this is third year electromagnetism. What is the what's magnetic moment of this? Okay, you cannot probably say it in one step, but how is the magnetic moment defined? Okay, it's the current, okay, times the area. So area is pi r squared. Now, how do I find the current? Well, if I just put an observer here and look at the amount of charge per unit time that's passing through a cross section there, okay, it's going to be this charge divided by the rotation period. So rotation period is the circumference, which is 2 pi r divided by v, right? So this is charge over delta t times pi r squared. Okay, so this is the classical magnetic moment. Okay, certain things will cancel, pi's cancel, one of the r's will cancel. So I end up with q over 2 times vr as the magnetic moment. Now you see I can relate that to the angular momentum because both of them have a v over r. So if I just take the angular momentum, multiply it by q over 2m, okay, that is the magnetic moment. Our magnetic moment is related to the angular momentum in the case of a classical particle, okay? Now, obviously, we are not doing classical mechanics here, and we have to somehow find the correct relation, which we cannot do at this time, unfortunately. But we'll have to trust, okay, people who do those calculations, that the relationship between mu, okay, so relativistic result is that I have this mu equal to a gamma times the angular momentum. Okay, so in this case S, the angular momentum. Okay, in fact, it's related vectorially. This is called gyromagnetic ratio. And this gamma is given as the charge over 2m. In fact, it's given as the electrical charge over 2m times g. Okay, so this thing is called very very creatively as g factor. Okay, so this is a g factor, which is the correction. So this is the classical term. So this g factor is the quantum mechanical, quantum electrodynamical correction to it. And it turns out that for the case of the electron, this is extremely close to, I should have this in my notes. This is one of the success stories of relativistic quantum mechanics, because this thing can be both calculated and also measured very accurately. So it's a good test of the theory. Yeah, okay. So this is equal to, for the electron, minus, okay, because electron has negative charge. So it's minus 2.002 319 ... to 14 significant figures. So this is one of the most accurately calculated objects in quantum mechanics, because just because it can also be measured approximately to that accuracy, to 14 significant figures. It fits beautifully. Okay, so this is very important. So each particle has its own g factor. Electron is a fundamental particle. It's not made up of anything else. So its g factor can be calculated like this. In the case so you may be hearing in the news, maybe I should talk a little bit about that, that the calculation for the muon, which is another fundamental particle, but the calculation is a little bit more difficult, so the accuracy is not that great, but the G factor, the anomalous G factor it's called, for the muon does not match the experimental value that well as we can see. Now that may be because there is a problem with the calculation or a problem with the experiment, or the calculation and the experiment are correct, in which case there is something missing in the theory. Yes?
E over 2m, is that m the relativistic mass or rest?
It's the rest mass. It's the rest mass of the electron. Okay? Okay, so that's that. But what's important is that we can just go over here and write down our Hamiltonian. H is equal to minus gamma, which includes all this G factor and everything, times SZ times B0. Okay? And then I can put this h bar over 2 in, so it's going to be minus gamma. SZ, remember, is h bar over 2 times sigma z. Did I erase them? Yes. Okay, times B0. Okay, so that's our Hamiltonian. And that indicates how the spin is going to change, because we have now the ordinary Schrödinger equation, I h bar del t, or this spin object, is equal to h times chi. Okay? All right, so let's construct a problem in which we see how this spin is changing as a function of time. So here comes our electron, okay? And suppose we measure its x component, okay? Now I measure its x component, so again, it can be plus h bar over 2 or minus h bar over 2. And suppose I take this electron, which has plus h bar over 2 spin in the x direction. And then, okay, I put it in a magnetic field in the z direction. Okay, so it passes through this magnetic field. Now, I am assuming it's going relatively slowly so that V cross B, the Lorentz force, is not so strong, but there is this magnetic field B0 in the z direction for some amount of time. So, okay, this is time equal to 0, and this is some time greater than 0, obviously. And now I am interested in finding the spin state of this object. Okay, so in which direction does the spin point after it goes through the magnetic field in the z direction? Okay, so let me just draw this. I have these x, y, and z directions. The magnetic field is in the z direction, so that's B0 z. And spin is originally in the x direction. I know that it's in the x direction. Well, I don't know that it's in the x direction, but I know that its x component is plus h bar over 2, because I can measure only one component, right? Now, under the effect of this magnetic field, this spin is going to change direction, okay? And I want to find out how it's going to change direction. All right, so let's just look at the problem. The initial state of the object is in the x direction. So this is my up x, right? Which is 1 over square root of 2, 1, 1. Now it's going to be influenced by this object. So I better find the eigenvalues, eigenstates of H. But it's very simple because it's just proportional to SZ, right? And I know that SZ has eigenvalues plus or minus H bar over 2. Sigma Z has eigenvalues plus or minus 1. So eigenvalues of H are going to be what? Eigenvalues. Okay. Okay. Plus or minus 1. Okay. Multiplied by gamma H bar be 0 over 2. Now you have to remember gamma is negative because it contains this G factor which has a minus sign in it. Okay. So the higher energy, let's call it E plus. The higher energy is minus gamma H bar be 0 over 2. And there's a lower energy which is plus gamma H bar be 0 over 2. Okay. So that's the energy scale. It's a two-level system. It has these two energies. And the one which corresponds to eigenvalue equal to plus 1, okay, is going to be the higher energy. Okay, so this will correspond to up Z. Okay, I'll just up. Okay, and this will correspond to down. Right? And this, remember, is 1, 0. This is associated with 0, 1. So my initial state is made up of, okay, so my psi, not psi, chi, at time equal to 0 is equal to 1 over square root of 2 up plus 1 over square root of 2 down, right? How does this change in time? Chi as a function of time is going to be 1 over square root of 2 interesting repetitive sound. Okay, 1 over square root of 2 times e to the upspin e plus minus e plus t I over h bar up plus 1 over root 2 e to the minus e minus, okay, t I over h bar downspin. All right, I'm just looking at, I just put in the time dependence associated with each one of these eigenstates of H. Okay, any questions? I'm running out of time. Yes, in fact, I have run out of time. So what we are going to do next time is we'll start from these vectors and look at something like what is the expectation value of Sx. Now that obviously is going to be well known at time equal to 0. What will this be at time equal to 0? Yes.
Hocam why, how did you find xt? I mean, where does it come from? How did you find the coefficients of?
Okay, this is x0, right?
Where did it come from?
Where did that come from? This is our initial state. These are the eigenstates. This state is
Okay, sorry.
1 over root 2, 1 over root 2, each one of those, okay? Now back to my question, what is this at time equal to 0? H bar over 2, right? Because initially we start with an state whose x component gives us h bar over 2, and at time equal to 0, obviously, if we measure the x component of the spin again, we are going to get plus h bar over 2. But now we are going to see, when we make this calculation, that this, at a later time, I'm going to get a smaller value for this expectation value, but a larger and larger expectation value for sy. So it will indicate that the spin, at least the xy component of the spin, is rotating on the xy plane. Okay, so that's where we'll start on Thursday.